All right, 16.2, limits. Given a function f with a discontinuity at a particular value of x equals c, how do you use limits to find the number f of x stays close to when x is kept close to c, but x is not equal to c? All right, so what is that question even saying? So I'm going to use this little example here to help you understand. So you can see that at x equals 2, we have a discontinuity, right? There's a hole here. Okay, and that's because if I were to set this denominator, equal to 0, if x is 2, we get an undefined function, right? So you can't have a 0 in your denominator. Okay, so when x equals 2, this thing's undefined, gives us this discontinuity. So what this is saying is if I'm heading towards c, so if I'm approaching this x value, or we'll call this x value c, if I'm approaching it from either the left or the right, approximately what value am I approaching for my limit, okay, or for my y-axis? Approximately what f value, okay, for function f, approximately what value am I getting out when I'm approaching c from either the right or the left? And it looks to me like it's approximately 7. And there's a couple of ways that we can figure it out. And one of them is to actually use the calculator. And I'm going to show you a few more ways. But why don't we just go ahead and see? So if I put this function into my calculator, oops. Oh, of course. Let's try that one more time. Okay, and so really, oh wait, let me divide this, so the whole thing. And I really care about 2, right? So I don't even have to graph this. Like, I already know what the graph looks like. So this is where I'm going to use my table of values. And I'm going to start at 2. And this is going to be kind of, oops, I'm going to start at 2. And it's going to be tricky. I'm going to go up by very, very, very small increments, something like that. So looking at my table of values, and what I've done here is I've ended up going a little too small, so it's recognizing that that's not really 7, that's 7.0003. You can see that, and this isn't really 2, it's 1.99999, but I've gone too small for my calculator to show you that. So what I see is that actually when x is 2, I'm getting an error because it's undefined. But all around that, so as I come from the left, right, 1.99999, however many 9s I have there, it looks like I'm approaching 7. It's really 7.00003. And then as I approach from the right over here, so that's really 2.000001, I'm getting to 6.99997. So what I can see is that as I approach 2, or my c here, my x equals c, from both the left and the right, even though it's discontinuous at 2, I can say, well, it's going to approach approximately 7. Okay, so that would be the limit as x approaches 2 of this function. So there I just used my calculator, but I could write something like the limit as x approaches 2 of this thing. How about I just call it f of x for right now? I'll come back and do a little bit more math with it. Is going to equal 7. And for that one, I used my calculator, which sometimes you'll want to use your calculator. Other times you won't be allowed your calculator, so you're going to have to figure that out. Okay, so let's give you a definition for a limit. And I'm going to write this kind of weird, but it's in a way so that way you can memorize it. So And you're going to see this again next year in calculus. L is the limit of f of x as x approaches c, if and only if L is the one number you can keep f of x arbitrarily close to just by keeping x close enough to c on both sides. This becomes very important in defining limits. On both sides, but not equal to c. The way that we actually write it is L equals, and the way that we say it too, the limit as x approaches c of f of x. Okay, so that's really important. So once again, L equals the limit as x approaches c of f of x. So maybe if that's hard for you to remember, you're going to want to write it down. L equals the limit as x approaches c of f of x. Okay, and so graphically, what does this mean? So let's see, I'll just draw some random graph here. It's going to look like this. I'm going to have some hole here, and then I'll continue on. Okay, and we're going to choose some place where, we'll choose some place where it's discontinued, which is this place right here. So I'm going to call that C. Okay, that's where x equals c. And then this discontinuity can be drawn off to the y-axis and has some output. We'll call that L, because that's actually the limit that we're looking for. And what we're saying is that if we pick some interval around L, so let's say from here down to, oh, I didn't do a good job with that. Make it a little smaller. It's got to actually touch it. Down to here. Then I can see that there are two corresponding x values. So if I pick some interval, pick any interval around L, f of x stays in here. If x is kept in this interval. That's a little bit more complicated probably than we need to worry about right now, but you can see that there's this interval around L and there's this interval around C. So if I pick any amount of number in this interval, okay, close to this limit, I'm going to be somewhere close to C. And maybe my drawing is not so close to C, but there's a better drawing in the book. Oh, and another thing is that it's important that we remember we're talking about both sides. Okay, so coming towards C from the right and coming towards C from the left. Okay, so when we're talking about the limit here, x approaches C. If it looks like this, then it's just from both left and right. There will be times when you just take one-sided limits, but for right now, the definition of limit for us is on both sides. Okay, so x approaches C from both the left and the right. That's what this notation right here means. Okay, so, excuse me, math. I'm choking on something. Mathematically, how can I find this limit? So I want to show you how to do that right now. So the first thing you want to do is you want to divide out your denominator. Okay, so I'm going to use synthetic division for that. Oh, I guess I don't need the plus, but whatever. Okay, so I divided in really nicely. That's great. And so really what I'm left with here then is the limit as x approaches c of f of x. Okay, and I've just divided out is really going to be the limit as x approaches, I shouldn't put c, I should put 2, of f of x is equal to the limit as x approaches 2 of what I have left here, because I've divided out my x minus 2 factor. And so I could say it's x squared minus 7x plus 17. And one very easy way to find this is to actually just sit there and plug in what x is approaching. And I think on this one it'll work. So it's 2 squared minus 7 times 2 plus 17. So we get 4 minus 14 plus 17. So that's actually negative 10 plus 17 is going to give me 7. So that's a way to do this mathematically, or you can use your calculator like we did originally. Okay, 2 ways of getting the same thing. Okay, so let's do another, I think, oh no, this one's not like that. This one's a little bit different. This one's just using graphically, so just like using your graphing calculator. So we're going to find each limit and use the definition of limit to explain your answer. Okay, so find each limit and use the definition of limit to explain your answers. So the limit as x approaches 1 of f of x. So remember, the definition said that you were approaching it from both the left and the right, and it wasn't where x equals c, it's as x approaches c, right? So it's as we get close to 1, not at 1. So as we get close to 1, we're looking at our graph here. From the left, it looks like I'm approaching 2, and from the right, it also looks like I'm approaching 2. F of 1 equals 1. But that's not what I care about, remember? And the definition of limit said not at x equals c, okay, but as you approach x equals c from the left and from the right. So let's go back to our definition. It also says that the limit is the one number you can keep f of x arbitrarily close to just by keeping x close enough to c on both sides, but not equal to c. Okay, so we're not looking for the actual value of f of 1. We're looking for the limit as this thing approaches 1. Okay, so we know that our limit's going to be 2. And we can say f of x stays close to 2 if x is close to 1, but not equal to 1. Okay? We don't care that f of 1 actually equals 1. We were asked for the limit. Second one, the limit as x approaches 2 of f of x. So as we approach 2, now this is a bit tricky. Again, I said as we approach from the left and from the right. Are we approaching one number? So again, L is the one number you can keep f of x arbitrarily close to by keeping x close to c on both sides. So let's look at that. As I come from the left, I'm approaching 3. But as I come from the right, I'm approaching 4. So it's either 3 or 4. Well, it can't be either because it's the one number. Okay? So this we call this does not exist. Or you could abbreviate it DNE. Okay, so we could say as we approach two, let's say x equals 2, from the left and right, f of x approaches two numbers, two different numbers. Okay, and it can only be one number. Okay, so let's try as x approaches 3. So the limit as x goes to 3, of f of x. So as I approach 3 from the left, I'm heading to 5 on my output. And as I approach 3 from the right, I'm also heading to 5. Okay, so we know that the limit is equal to 5. We can say that f of x stays close to 5 if x is kept close to 3, but not equal to 3. Let's just put a not equal to. All right, D, the limit as x approaches 4 of f of x. So again, as we approach 4 from the left, we're headed to 3, and from the right, we're also headed to 3. So same kind of reasoning. So this is going to equal 3. F of x stays close to 3 if x is kept close to 4, but not equal to 4. And E, what happens as we approach 5? Okay, so the limit as x approaches 5 of f of x. Well, as I approach from the left, looks like I'm heading straight up, and as I approach from 6, I'm also headed straight up. So that means that there's a vertical asymptote here at 5. And there's two ways that you can answer this. You can say that it does not exist, which I think this book is going to say it doesn't exist, or you can say infinity. Okay, infinity is not really a number though, so it's hard to make an argument that the limit equals infinity. It's going on up and up and up forever, but again, infinity is not truly a number. So we can say something that the limit as x heads to 5 of f of x does not exist. I'll just put that. So we can say because there's a vertical asymptote, I'll abbreviate VA, but if you don't know that, then you should write it all out. F of x becomes infinite there. So there is no number f of x stays close to if x is kept close to 5. So what you just witnessed, I'm going to add a little more. So you just talked about limits graphically, and we're going to continue talking about limits graphically. I'm going to do a couple examples not from the textbook, and we're going to find these limits. Now, these limits are different because they are approaching infinity and negative infinity. So this is the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. Okay, so that means infinity is basically the numbers get really, really big. Negative infinity, the numbers get really, really small. All right, so here's the function. Here's the graph of the function. Okay, and for each of these, we're going to find the limit as x goes to infinity of f of x. And then we're going to go the other direction, the limit as x goes to negative infinity of f of x. That's a bad infinity sign. Okay, so right here, this is your x-axis. I know these weren't perfect pictures. I got them, I don't really even know where I got them from, but I found them. So this is your x-axis, this is your y-axis. Okay, so this is the function f of x. So as x gets really, really big or goes to infinity, approximately, what is this function f of x approaching? Well, it appears to be approaching this horizontal asymptote at y equals 1. So as x goes to infinity, as it gets really, really big, this appears to be approaching y equals 1. And then going the other direction, the limit as x goes to negative infinity, or as it gets really, really small, so going this way on the x-axis, well, again, this appears to be approaching some horizontal asymptote that appears to be negative 1. So those are pretty easy. Graphing these or looking at limits graphically is a pretty simple concept. All right, B. Okay, so this time you don't have a function, but again, this here's your y-axis. This here appears to be your x-axis. You've got two lines here. This horizontal line is called P, and this horizontal line would be like y equals Q. Okay, so y equals P, y equals Q. All right, we're going to do the exact same thing. So the limit as x approaches infinity, we'll call this f of x, even though it doesn't say that it's f of x, we'll call it f of x. So as x gets really, really big, so this is something you maybe haven't seen before. Notice that this is oscillating, right? It's going up and down and up and down and up and down until it's getting really, really close to just being on P. So the limit as x approaches infinity, as it gets really, really big, looks like it's going to start getting close to this line P. So we'll call that equals P. And then the limit as we go the other direction, so as x goes to negative infinity of f of x. Well, now this one, it crossed Q, went up, maxed out, and started to come back down, and looks like it's not going to cross it, but it's going to, in this case, Q is going to be what appears to be like a horizontal asymptote out to the far negative infinity area. So we'll call that Q. So you can see that these are just getting really, really close to some output, but they don't necessarily have to equal that output. Okay, we'll do the same one for C. So the limit as x goes to infinity of f of x. Okay, so as x gets really, really big, now here's something interesting. Where does the y appear to be going? It appears to just keep getting smaller and smaller and smaller and smaller. So this would be an example where you would say that this one equals negative infinity or does not exist. I think in this case it would probably be best to say it just gets really, really small. So that's what we're basically saying here. This is just getting really, really small. And the limit, as x goes to negative infinity of f of x, well, this is going to get really, really big, right? As x gets really, really small, f of x is going bigger and bigger and bigger and bigger. So you would equate that, even though you can't really say that it equals infinity, you would say that it's just getting really, really big, and to do that, you would have to equate it to infinity. Doesn't really equal a number, it equals an idea that it's getting bigger and bigger and bigger. Okay, so here's one. Oops, I copied this very poorly. All right, so this one is just constantly oscillating back and forth, back and forth, back and forth. You should be very familiar with f of x equals cosine of x. And so does it ever appear to be approaching, does your output ever appear to be approaching one number? It doesn't, because it's constantly oscillating, right? And this is going to continue forever. because it is a periodic or a cyclical function. So the limit as x approaches the limit as x approaches infinity, so as x gets really, really big, again, here's your x-axis, here's your y-axis. As x gets really, really big, the limit's not going to exist because it's never approaching just one number. It's never approaching just one output. And same as we go really, really small. So the limit as x goes to negative infinity of f of x also will not exist because as x gets really, really small, this thing just keeps oscillating exactly as it was. See how these oscillations are a bit different than b? These oscillations got smaller and smaller and smaller so that they were actually approaching that output of p. These don't, right? They just keep going exactly the same amount above and below the x-axis. So they don't approach like one specific output. So these are the answers. I didn't do a good job of copying that. Okay, so at this point, you should be good to go on finding limits graphically. Okay, now let's talk about finding limits algebraically. So finding them graphically is pretty simple. You just look at the graph. Algebraically is going to be a little bit more challenging. You're going to have to really use some of your algebra that you've learned about. So recall, a function f is continuous at x equals a. So at whatever that x value is, we were calling it c before. It might be a certain number like 5. Provided the graph of y equals f of x does not have any holes, jumps, or breaks, discontinuities at x equals a. That is, the function's connected at x equals a. Okay? So we're talking about continuous functions here. Now, if f is continuous at x equals a, then the limit as x approaches a of f of x is just f of a. So, for example, what am I talking about here? We'll call this some x equals a. Okay, so this is my x-axis. This is my y-axis. I have some function here. Let's just make it some parabola. And notice that it's continuous. So whatever the value is at a, at x equals a, whatever that output is, that's what the limit is, okay? Because I'm approaching, as I approach a from the left and the right, I basically approach this output. We'll call it, what should I call it? L. We approach this output L from top and bottom. Okay, so that's all that that's saying. Now, if f is continuous at x equals a, then basically the limit is going to be exactly, if you were to plug a into the function, that limit is going to be exactly what you get out. Okay, and that's what this says. That is the value of the limit equals the value of the function. All right, so as a result, almost all the functions you're familiar with are continuous at every number in their domain. So don't forget about restricted domains. That's where things are going to be discontinuous. In particular, the following functions and any combinations of these functions are continuous at every point in their domain. It's got to be in their domain. So all of these functions that we're going to be working with, polynomial functions, rational functions, radical functions, exponential functions, logarithmic functions. Hence, to find a limit of any of the above function as x approaches a, we simply evaluate that function at x equals a. And usually it'll work, but sometimes it doesn't. So here's an example of where it's very easy and it works very, very quickly, okay? So we basically say the limit as x approaches 3 of this thing is equal to, and all you do is you actually plug 3 in for x. So I plug 3 in, so I'm just evaluating this because this is a continuous function. Oops, not x. I plug 3 in like I just said I was going to do. This is a continuous function. We know that there's no holes. Okay, so I've got 9 plus 12 plus 1, or 10 plus 12 is 22. All right, now let's try that on the next one. So let's go ahead and let's find the limit here as x approaches 1. Well, what's going to happen? You end up with this thing, and we actually call this the indeterminate form. 0 over 0 is one of the indeterminate forms. It can't be determined what this is, right? You can think of this as, oh my god, my denominator is 0, it's undefined. We'll talk more about indeterminate form next year. Okay, so what do we do at this point? We try and we use our algebra, because this is not an acceptable answer. This is telling me that there is actually a hole or some type of discontinuity at x equals 1. Now I know that there's a hole, and this is why I know that. I'm going to use my algebra to factor this. So in my numerator, that is a difference of 2 squares, so that's x plus 1, x minus 1. My denominator is just x minus 1. See how in numerator and denominator I have a common factor? That tells me that at x equals 1, because if I set this equal to 0 and solve, I would get x equals 1. So at x equals 1, there's going to be a hole. Okay? We have what we call a removable discontinuity. So now I just evaluate the limit as x approaches 1 of this. Okay, so what this is going to give me is the limit as x approaches 1 of x plus 1. I'll go ahead and I'll write it out one more time. Okay, of that is going to basically, now I can just evaluate it. 1 plus 1, which is 2. So what this is there's some graph. I'm not 100%. This is going to be a linear graph. It's actually going to look like this. It should look like x plus 1, so it's going to have that. And then at 1 on the x-axis, it would have a hole. And then it's going to, when we actually evaluate it, so well, we can't evaluate the actual function, but when we do plug in 1 into the reduced function, at 1 I have an output of 2. However, there's a hole there. So what it's saying is, this is a removable discontinuity. There's a hole, okay? But at 1, if I come along this graph from both the left and the right, I'm going to approach an output of 2. Okay, so the answer here is 2. And you can double check that on your graphing calculator when you get stuck on these. Sometimes you will. All right, here's another one. So what I always do when I'm doing these is I try to evaluate them first. So I'm just going to go ahead and say, oh, let me go ahead and plug in 2, because this is the limit as x approaches 2. So I go to this over 2. Oops, that's minus 2. And you can see, once again, this is 4 divided by 2, so it's 2 minus 2, which is 0 over 0. Once again, I get this thing called indeterminate form. Okay, so this means I have to simplify this. This is not the easiest thing to simplify. So in order to try and simplify this, I don't even know if I can do factoring yet. I'm going to try and simplify the numerator first, then work with the denominator, dividing that into the numerator. So I'm going to keep writing this as the limit as x approaches 2. Now this is x plus 2 over x. This I'm going to go ahead and give it a common denominator of x, so it'll be minus 2x over x, all over x minus 2. And I'm going to keep writing the limit there until I actually evaluate this limit. So I'll go to the side now, equals the limit as x approaches 2. So let's see, this is going to be x minus 2x, which is a negative x, plus 2 over x. And then that's divided by x minus 2. Well, we don't divide fractions. Instead, we multiply by the reciprocal. Now, I can turn this, let's see, do I want to do that? Multiply by the reciprocal. I messed that up. Multiply by the reciprocal. Don't divide by x minus 2. Multiply by its reciprocal. Sorry about that. I said it, but I didn't do it. Okay, now when I look at this, I say to myself, hey, I could probably factor out a negative 1 and get that. So this is going to be equal to the limit as x approaches 2. I'm going to factor out a negative 1 for my numerator here. which will leave me with x minus 2 over x times, and then 1 over x minus 2. Notice now that the x minus 2's reduce, and I'm going to come back over here. So that's the limit as x approaches 2 of, let's see, negative 1 over x. Okay, and now I can evaluate this because I've got it nice and simplified. So if I plug 2 in, I'm going to get a negative 1/2. Okay, so using all the algebra we've ever learned about. All right, so now I've got one that you're really going to have to think back about. So we're going to let f of x equal 1 over x. And we want to find the limit as x approaches infinity and the limit as x approaches negative infinity. All right, well, let's think about this. So the limit as x approaches infinity of 1 over x will really equal 1 over infinity, right? If I were to plug in infinity, well, infinity is not a number. This doesn't really make any sense. You can think of this a couple different ways, though. The first way is to think, what number, if I take, for example, 1 and I divide it by 1, okay, the answer is going to be 1. Now, let's start making this bottom, my denominator, become larger and larger and larger. So if I divide by 10, I get 0.1. If I divide by 100, I get 0.01. If I divide by 1,000, I get 0.001. If I divide by 10,000, I get 0.0001, I think. You get my point. This is going to get really, really, really small as the denominator gets larger and larger and larger. So that's one way to think about that. And then probably thinking about this graphically has always helped me. So hopefully you're familiar with the function f of x equals 1 over x. That is a hyperbola, right? It's a rational function centered at the origin. So it looks like this. Well, this is my x and this is my y-axis. So as x gets really, really large, what's happening to this graph? It is approaching the x-axis, which happens to be an asymptote. So it is approaching 0. So this actually does go to 0. Now let's talk about the limit as x approaches negative infinity of 1 over x. Well, that's really 1 over negative infinity. Again, negative infinity is not a number, so this doesn't really make much sense. But now let's think about this as a concept. 1 divided by numbers that are getting smaller and smaller and smaller and smaller as you go on to infinity, right? So actually I should say they're getting bigger and bigger and bigger in the infinity direction. Okay, so in the negative, in the negative direction. They're getting bigger and bigger and bigger in the negative direction. I apologize. Okay, so let's think about that. So this would be like dividing 1 by negative 1, which would give me negative 1. 1 divided by negative 10 would give me negative 0.1. 1 divided by negative 100 would give me negative 0.01. 1 divided by negative 1,000 would give me negative 0.001, and so on. So you can see that this is actually becoming a very small number in the negative direction. And you can also see it from the graph here. As x gets really, really small, this thing is, again, approaching 0. It's approaching that horizontal asymptote, which is the x-axis. Now, these are very important. So you would really help yourself out if you memorize these. So basically what you want to know is that the limit as x goes to infinity of 1 over x is equal to 0, and the limit as x goes to negative infinity of 1 over x is also equal to 0. Or basically have this graph memorized, because you're going to need to use this every time that you're finding, or most of the time that you're finding limits involving infinity, and you don't already have a graph. Okay, let me clarify one more thing with you guys here. So this here says the limit as x goes to infinity of 1 over x. 1 is a constant over a variable x, right? So anytime you have any constant up here, you're going to get the same result. So if this was the limit as x approaches infinity of 5 over x, it's still going to go to 0 because 5 is going to stay the same while the denominator is getting bigger and bigger and bigger, hence making the quotient smaller and smaller and smaller. Okay, so we're going to use that to help us on this next problem. So this one we got this rational function, and we're going to find the limit as x approaches infinity and as x approaches negative infinity. Now there's a trick to these, and if you can remember this trick, it's going to make your life a lot easier. And of course, you could always put this into your graphing calculator and figure it out there by maybe using your trace or your table functions in your graphing calculator. But you're not always going to be allowed to use your graphing calculator, especially on like AP exams. So you want to be able to do this without your graphing calculator. So let's see, a few pages back, I think this is the second to last page in your packet, I printed off, well, I did a really bad job, but I copied this out of an old pre-calculus book that I used to have. And I feel like this is really, really helpful. And we'll go back over this one more time. But I want you right now to look at number 4. So this only happens if x is approaching infinity or negative infinity. Then one thing that you can do to make your job algebraically easier is to divide the numerator and the denominator by the highest power of x in the denominator. I'm going to highlight that. So if x is approaching infinity or negative infinity, divide the numerator and denominator by the highest power of x in the denominator. Okay, so any time that your limit or your x is approaching infinity or negative infinity, you want to kind of come to this tool. All right, and that's exactly what's happening here. So let's start with as x goes to infinity. Well, my highest power of x in my denominator is x cubed. So that means I'm going to divide everything in the numerator by x cubed and everything in the denominator by x cubed. So I'll do that first. So it's going to be 3x cubed. Oops, got to put the limit there. It's going to equal the limit as x goes to infinity of 3x cubed divided by x cubed, because that's the highest power of x in the denominator, plus x squared divided by x cubed, minus 5 divided by x cubed. And then same thing in the denominator, 2x cubed divided by x cubed, minus x divided by x cubed, plus, and then 1 divided by x cubed. Okay, so things are going to start simplifying now. So this is going to be the limit as x goes to infinity. Now the x cubes here reduce, so I'm just left with a 3. You have an x squared over an x cubed, so really this becomes a 1 and this becomes just x. So it's going to be plus 1 over x minus, and then this, I can't simplify anything, so I'll just put 5 over x cubed. And then over here, you're going to have, let's see, the x cubes go away, so you're going to have a 2. X to the first, x cubed, this is going to reduce to a 1, and this will reduce to an x squared. So, oops, that's minus. Plus, and then you can't simplify that one at all, x cubed. All right, so let's think about this. As these things go to infinity, so 3 is going to stay the same, but this will become 1 over infinity. And what is 1 over infinity? 1 divided by infinity, right? As x gets really, really big, this becomes 0. So I'm going to put like a little arrow and just show that this goes to 0. Then this would be minus 5 over infinity cubed. Well, infinity cubed is just infinity, right? It's just getting bigger and bigger and bigger. So once again, we're back to a constant over x, right? Or over infinity, which is going to also go to 0. My denominator, okay, I got a 2. I got 1 over infinity squared, which again, that's a constant over infinity. That's going to go to 0. And then plus 1 over infinity cubed, which again goes to 0. So I've got 3 over 2. That's going to be my limit. Now let's do it as it goes to negative infinity. So the limit as x goes to negative infinity, what do you think is going to happen here? Oops. Okay, so this is going to be the limit as x goes to infinity. And I'm going to do I basically am going to end up with exactly this thing. Oops, negative infinity. I'm basically going to end up with exactly this thing, right? So I'm still going to have 3 plus, now this will be 1 over negative infinity and minus 5 over negative infinity cubed. None of this really matters because this is just going to go to 0, right? And then on the denominator, I'm going to have that 2. And what's going to happen with both of these? They're also going to go to 0. So minus 1 over infinity squared, negative infinity squared, which doesn't really matter whether it's positive or negative, plus 1 over, and then again, negative infinity cubed. These both go to 0. So once again, I'm just left with 3 halves. All right, let's do that again. So anytime I'm looking at limits where my x value is approaching infinity or negative infinity, I can use that little trick. If I don't know what this thing looks like, if I know what this looks like, then it's not a big deal, and I can just think about it graphically and come up with an answer, like if it was a parabola or a line. But in this case, it doesn't look too easy to factor. So, right, because I'd have to have like a difference of 2 cubes here. That's not going to work out so well for me. This isn't going to factor perfectly, so I can do some long or synthetic division, which we will get to, but we won't do it just yet. So again, I'm going to use that little trick number 4, which basically says find the highest degree of the denominator and divide numerator and denominator by that highest degree of your variable. All right, so the limit as x goes to infinity of f of x here. Well, let's simplify it first, right? So my highest degree is x cubed. Numerator and denominator get simplified by that. So this is going to be the limit as x goes to infinity. Now you'll do x squared over x cubed plus x over x cubed plus 3 over x cubed all over, and then 5x cubed divided by x cubed minus 1 divided by x cubed. Simplifying, this becomes 1 over x. This becomes 1 over x squared. This becomes 3. We'll just leave that as 3 over x cubed. Can't simplify it. This basically just becomes 5 minus 1 over x cubed. Now plugging an infinity into this, you'll have 1 over infinity plus 1 over infinity squared plus 3 over infinity cubed. Now what's happening with all 3 of these? They're all going to 0. So right away in my numerator, it's 0. Let's just make sure that my denominator is not 0 as well, because then I'll have an indeterminate form. I'll have a problem. All right, so this is going to be 5 minus 1 over infinity cubed. 1 over infinity cubed goes to 0, so this is going to be 5. Well, what is 0 divided by 5? That, in fact, is 0. And if I were to do the same thing with negative infinity, right, was it going to change anything at all? No, that's also going to give me it's also going to give me 0. Okay, and let's do one more here of these types anyways. Don't worry, we got plenty of problems to do. So, one more time, I've got a rational function. None of this looks very easy to factor. No, not at all. And therefore, it's to factor and reduce or to try and do long division here. Not going to be too easy, so I'm not even going to bother with that. I'm just going to go ahead and do that same exact trick that I've been doing. It's not really a trick. You're basically just simplifying. You're dividing numerator and denominator by the exact same number. And so it's really like dividing by 1. You're just simplifying this a bit. Okay, so the highest degree in the denominator is x squared, which means I would divide everything by x squared. So the limit as x goes to infinity of f of x will equal the limit as x goes to infinity. I know I do my infinity signs terrible. I'm going to divide everything by x squared. So I'm going to have x cubed divided by x squared minus x squared divided by x squared plus 3 over x squared over 3x squared divided by x squared plus x divided by x squared minus 5 over x squared. Okay, so this one now is going to be, I can just go ahead and start, oh no, I'll simplify first. The limit as x goes to infinity, this just becomes x, the first term. Next one becomes minus 1, and then this right here will go to 0, right? So plus 3 over x squared is going to end up going to 0, but we'll talk about that in a minute. All over, now this reduces to just 3 plus, and that's going to give me 1 over x minus 5 over x squared. Okay, so now I'll go ahead and I'll plug in that infinity. So I'm going to have infinity minus 1 plus 3 over infinity squared, and then 3 plus 1 over infinity minus 5 over infinity squared. Okay, now there's nothing that I can do about infinity or minus 1, but this 3 divided by infinity squared, that's going to go to 0. I've got a 3 here, which will stay, and then this will go to both of these two terms, end up going to 0. So I've got infinity minus 1. Let's see, I'm going to write that out. Infinity, if I could write infinity, that would be nice. Infinity minus 1 over 3. So what is the largest number you can think of minus 1 divided by 3? It's still going to be a really large number, right? So this basically is going to equal infinity. Infinity wins here. Okay, the 1 and the 3 don't do anything to it. Now from here, let's think about, instead of plugging in infinity, let's think about if I wanted to do the limit as x goes to negative infinity. But I'm just going to jump in right here. Okay, so of f of x equals, and I'll go negative infinity minus 1 plus 0, right, over 3 plus 0. So really, you've got a really small number, or huge in the negative direction. You're subtracting 1 from it and dividing by 3. Well, the subtracting 1 divided by 3 isn't going to do much to that huge number. Like imagine if I had, well, that's not a huge number, it's a really small number, but let's go back to this positive infinity because I want to talk about my bank account looking like this, right? Let's say I had positive gajillions of dollars. If I subtract 1, it's not really doing much to it, right? Okay? All right, maybe dividing by 3, if I had to give a third of it to somebody, it would. But still, this isn't doing much. This is just a really huge number, so it's going to infinity. This is a really small number, so it's going to negative infinity. All right, example 2. So we have the graph of this rational function. We're going to simplify the fraction in the equation for f of x by substituting 3 into the simplified equation, and then find the limit f of x. Does the result agree with the graph? First, we have to simplify the equation. So I think we're going to do like what we did on our first, that initial function that I showed you. We should do some synthetic division. I have to divide out that x minus 3. Otherwise, if I plug 3 into this, it's going to just give me an undefined. Okay, so this actually leaves me with x squared minus 2x plus 2. Okay, or I can say this, f of x equals this, where x does not equal 3. It's important to write that. And then I can say that, so now I'm just going to substitute 3 into the simplified equation to find the limit as x approaches 3 of f of x. So I can say L equals the limit as x approaches 3, and I'm going to do that of x squared minus 2x plus 2. And really, usually, if it's not going to make it undefined, then what you can do is you can just go straight over here and you can plug in 3. So if I plug 3 in, I'm going to end up with 5. So that's my limit right there. Notice that I write it in limit notation until I actually plug something in. Okay, B is going to get a little bit more tricky. So in what interval must x be kept in order for f of x to stay within 0.1 unit of the limit? Okay, so to be within 0.1 unit of the limit, basically I want to make sure that my output is either 0.1 bigger than the limit or 0.1 smaller than the limit. And the limit right now is 5. So I'm going to take this function and I'm going to set it equal to 5.1, or I'm going to set it equal to 4.9. So I care where f of x is either going to be 5.1 or f of x is going to be 4.9. Okay, so I'm just going to take the simplified version of my function and I'm going to set up 2 equations. And then I can do a whole bunch of simplifying, well, some simplifying. I can put these things into standard form. And then I can actually use the quadratic formula to find my answers. And these answers have to make sense, right? So they have to be close to 3. So you're going to end up with 2 answers here. You get, here I'll give you both of them, but I would encourage you to use the quadratic formula. I do not encourage you to just sit here and copy down my answers. Right now, go back, use the quadratic formula. You'll see that you get 2 specific answers. But it won't make any sense to get this -1 because that's nowhere near 3. So we're not going to use that answer. On this side, you'll get x equals and again, we're trying to keep it close to 3, so using this answer would not make any sense. Okay, so you can use these 2 numbers to say, well, x should be somewhere in between. We'll use the 2.9748 and the 3.0248. Okay, moving on to C. We're going to choose a value of x in the interval in part B and show that f of x really is within 0.1 unit of the limit for this value of x. So within this interval, I could use, how about 3.01? Okay. If I do f of 3.01, just plugging it back into my equation, and that's going to give me 5.0401, which is within 0.1 units of 5. Okay, and then the last one. Would the procedure in parts B and C work for any interval containing L, no matter how small? And yes, it will, because f of x stays arbitrarily close to 5 when x is close to 3 but not equal to 3. So where can I answer that? I'm out of room here. How about we just go here? Yes. F of x stays arbitrarily close to 5 when x is close or is kept close to 3 but not equal to 3. Good enough. I gave myself so much room, I thought, but obviously not enough room here. Okay, moving on to example 3. You have the graph of the rational function. The first thing we're going to do is write the fraction in the equation for g of x in mixed number form. Okay, so write the fraction, I think it should be of the equation, for g of x in mixed number form. I should have enough room to do this, but maybe, why don't I do a up here, just to make sure. So you notice here you've got some asymptotes, right? You've got that vertical asymptote at x equals 3, but you've also got this parabola-looking asymptote, or like we call them slant asymptotes or curved asymptotes. And so that comes from when we divide x minus 3 into this. Okay, so we end up with, let's see, we're going to do 3 into 1, negative 5, 8, negative 5. So see, x minus 3 is not actually a factor. I did something wrong here. Oh, 2 times 3 is not 15. It is 6. Thank you. But still, we end up with a fraction left, or we end up with something left over. So we know that x minus 3 is not actually a factor of this thing. Okay, so what we end up with here, we'll still have x squared minus 2x plus 2 plus, and then we have 1 over x minus 3. Okay. So how does the remainder fraction in the mixed number form of g of x reveal that there is a vertical asymptote at x equals 3 and thus no value of the limit as x approaches 3 of g of x? So I'm going to answer B down here. Well, we know that as x approaches 3, this piece right here, as x gets closer and closer and closer to 3. So let's say, for example, okay, I've decided to use my calculator because I was rambling and nobody would probably even know what I was talking about. So let's just pretend I'm approaching 3. Let's say I'm starting at 4. Okay, so I plug in 4 into this equation and I end up with 1. Okay, and then as I put 3.9. It's getting bigger, right? 3.8, it's getting bigger. 3.7, it's getting bigger, right? Because I'm taking 1 and dividing it by a smaller number. Look, at 3.1, it's up to 10. Well, and imagine if this was like, if I was going by hundreds of thousands. Okay, this number is just going to keep getting bigger and bigger and bigger. So really, this thing ends up going to infinity. So that's why we end up with this vertical asymptote. Okay, we don't end up with a hole or a discontinuity. We end up with it is a discontinuity, it's a type of discontinuity, but a vertical asymptote instead of just a hole. Okay, so we can say that as x approaches 3, y equals 1 over x minus 3 becomes infinite. In other words, the limit as x approaches 3 of 1 over x minus 3 equals infinity. Okay, and again, you can't really say equals infinity, but just so that you have it becomes infinite. Therefore, we have a vertical asymptote. So that's one way that you can determine if you have a vertical asymptote somewhere in a graph. Maybe you're not allowed your graphing calculator. Hey, do I have a vertical asymptote there? Do I have a hole there? Right? The last ones, a couple that we did do, when you divided, you didn't have a remainder. So you didn't end up with a vertical asymptote, you just ended up with a hole. All right, looking at C, how is the polynomial part of the mixed number form of g of x related to the graph of function g? And hopefully you can remember this, I think we did this in the beginning of the year, but the rest of this is going to be your other asymptote. It's going to give you this parabola asymptote, right? So the x squared minus 2x plus 2 is the polynomial part and is the curved asymptote for the graph. And so graphically, if you were looking at this, you might ask yourself, hey, what's the limit as x approaches 3? Just looking at the graph, you should say to yourself, all right, well, at x equals 3, we have this vertical asymptote, so there's not going to be a limit as x approaches 3 because from the left, I'm going one direction, and from the right, I'm going another direction, right? So this one's going to like negative infinity, this one's going to positive infinity, so there's no limit. The limit does not exist at x equals 3. Okay, example 4. All right, so given that the limit as x approaches 1 of h of x is equal to h of 1. Okay, so here's h of x. You plug 1 in, right, and you get 2. So notice no discontinuity. Find an interval of x values for which h of x stays within 0.1 unit of h of 1 when x is kept in this interval, but x is not equal to 1. Illustrate your answer on a copy, or this will be our copy, of figure 16.2f. Choose a value of x in this interval and demonstrate numerically that this value of x gives a value of h of x that is really within 0. So this is very, very much like this example, okay, where we picked a number within 0.1 unit of f of x, and then later on we showed that we could pick some number x, plug it in, and it'll keep us close to the limit. So that's exactly what we're going to do here. Very similar, just way more wordy, not as like full of steps. So at 1, h of x is 2. So keeping it within 0.1 unit, I either want 2.1 or 1.9. So I'm going to let h of x equal 2.1 or 1.9. Okay, and then I'm going to set up those two different equations. So 2 to the x equals 2.1, or 2 to the x equals 1.9. Okay, so solving this, now I got to solve for x, so I need to use logarithms. So I'm going to have x log of 2 equals log of 2.1, solving for x. And we get approximately 1.0703. So that's one of them. And then doing that on the other side. Solving, we end up with x equals log of 1.9 divided by log of 2, which gives us approximately 0.9259. Okay, and so we should keep x in between 0.9259 or 1.0703. Okay, that'll keep it within 0.1 unit of 2. So let's choose some x now for the second part of this. Let's choose some x that's in between these. So how about I let x be 1.04? Okay, so if I let x equal 1.04, let's just prove that we actually are within 0.1 units of 2. So plugging that in, you get 2 to the 1.04, which is 2.0562. And obviously this is within 0.1 unit of 2. Okay, now this is an example of where if you were given this and you had to find the limit as x approached 1, it would actually, the limit is actually equal to h of 1 because there's no discontinuity. There's nothing undefined. So I can always say that the limit as x goes to 1 of h of x, for this example, will equal h of 1, which is actually 2, since h of x is defined at x equals 1. Okay, so that's the difference between when can I just plug it in and when am I going to have to do some other algebraic stuff or maybe even graph it to understand where the limit is. Okay, oh, and then I have to actually show I was supposed to illustrate your answer on a copy of 16.2, so I kind of missed this. Sorry. Illustrate my answer. So illustrate this answer right here, okay, on a copy. So we're just going to go ahead and use this copy right here. So I know that I can choose any number within 0.1, and I'm just going to be kind of messy about it, but this is 1.9. This is 2.1, right? And now those numbers correspond with different x values. Okay, and those x values we solved for. They were right here. So 0.9259 or 1.0703. And then I chose something that was approximately right here, and it did. It corresponded with something just right above 2. Okay, some more limit vocabulary that you might be exposed to. You might see something like the limit as x approaches c plus of f of x. So this means limit as x approaches c from the right. So that would be a one-sided limit. You might also see the limit as x approaches c minus of f of x. Okay, so when you see that, that's the limit as x approaches c from the left. Okay, so those are one-sided limits. Sometimes you'll just want to know from one side. Okay, we're going to go back and we're going to now talk about this section that we already looked at, number 4. These are called the techniques for evaluating the limit of a rational function. Notice you've got a function in the numerator and a function in the denominator, so that's a rational function. This is a quotient of functions. Okay, so number 1, if possible, use the quotient theorem for limits, which basically says, let me give you an example here. So this could be like the limit as x approaches 5 of, let's just do x squared plus 2 over x plus 1. Okay, I made that up. So all this would be to say, take the limit of the numerator as x goes to 5 and put that over the limit of the denominator as x goes to 5. So notice that I can plug 5 in here and I get 27. And here I can plug 5 in and I get 6. So 27 over 6, or reducing that, what do you get? 9/2. Okay, so it's that simple. So that's what the quotient theorem for limits is. It's basically saying if you can just go straight forward and evaluate this. Okay, and I really can. I didn't even have to break it up like this. I could have just went straight forward. Okay, but that is the quotient theorem for limits, is where you take the numerator, you find the limit of that, take the denominator, find the limit of that, and then put them together. Now, what happens, for example, if I do this, and I get 0 over 0? Well, that's what number 2 is talking about. So that indeterminate form that I keep mentioning. So if the limit of f of x equals 0 and the limit of g of x equals 0, notice f of x is in the numerator, g of x is in the denominator, you can try the following techniques. First of all, you can factor both numerator and denominator and reduce to the lowest term. This is going to result, this means that you have basically, if you can do this, if you can factor it and reduce, that basically means that you have a removable discontinuity. Or a hole. Okay? Now, if f of x or g of x involves a square root, try multiplying both f of x and g of x by the conjugate of the square root expression. So for example, if you had, I don't know, the square root of 2, you can multiply top and bottom by the square root of 2. If you had the square root of 2 and then minus 1, the conjugate of that would be the square root of 2 plus 1. Okay? So those are a couple of techniques that you can try. Okay? Next, if the limit of f of x does not equal 0 and the limit of g of x does equal 0, right? So basically your denominator is equal to 0, your numerator is not. And you don't have this as like x is approaching infinity, because that's a whole different scenario. Okay? So this is number 4. That's separate from what we're doing right here. Then either statement A or statement B below is true. Maybe the limit does not exist. Or maybe it's approaching infinity, or it's approaching a negative infinity. Okay, number 4 we went over. So basically this was kind of a little trick that you could use. It's not a trick. You're just dividing out the highest degree of your variable from the denominator. And it's basically it's reducing all of the terms. Okay, so then you can get down to, hopefully that definition, the limit as x approaches infinity of some constant over x goes to 0. And number 5 is not very helpful, but if all else fails, you can guess, now this is the limit as x approaches infinity of f of x over g of x by evaluating f of x over g of x for very large values of x, right? Because x is going to infinity. And you can guess the limit as x approaches c by evaluating f of x over g of x for x values very near x equals c. So for example, if x equaled 5, maybe you do 5.1 and 4.999, and you just do those on your graphing calculator really quickly, and hopefully you should be able to figure out what the value is approaching. These limits can also be guessed by using a graphing calculator. So if all else fails, hopefully you're allowed a graphing calculator, and that's what I do. I just graph it and I examine the graph. Okay, for very large values of x, or for x values very near x equals c. Okay? And remember, the graphing calculator might not show the points of discontinuity. So that's where you want to go into your table and you want to look for, hey, are there any discontinuities in here? That's where, again, if it's like at x equals 5, maybe you want to look at 5.001 and 4.99999 and just see, like, hey, what's actually happening close to that x value of 5. All right, so I found a few more problems for us to work out. I'm not going to do every single one of these, but I'll do a few of them. And then maybe you can do some of them for your homework. And some of these, you're just going to need a calculator for. You can't always find the limit algebraically, but I'll try and give you some tricks. All right, so the first one here, the limit as x approaches -1. Well, notice if I put -1 in there, it's not undefined. Okay, I can plug -1 in, and I can actually get a number that's not undefined. So that's exactly what I'm going to do. So I'm going to basically say, well, this is going to be the limit as x approaches, actually, I'm not even going to do that. I don't have to, because I'm just going to start plugging numbers in. So I'm not even going to use limit notation anymore. You want to use limit notation if you're like simplifying still, and I'll give you some examples of that. But here I can just actually plug -1 in, because I'm just going to evaluate it. Okay, so that's going to be 1 plus 1 over -2. Or in other words, 2 over negative 2, which is negative 1. That would be my limit. Okay. Why don't we do, let me skip down to number 6. I'll let you do number 5. So why don't you do this one after I do number 6? I'll do a more complicated one. So again, I plug negative 3 in. Oh, that's a problem, right? This is going to be undefined. Can I simplify? So yeah, you can always use synthetic division if it's complicated, but something like this, I can factor this. This is super easy. So this is really x plus 3 and x plus 3. Sorry, there's loud teachers in the hallway. Over x plus 3, which these now reduce. Oh, and I'm concentrating on the teachers. We should have limit notation being used. So this is really going to be the limit as x approaches 3 of this stuff that I'm simplifying, which is now going to be, now at this point I can just, because I've simplified, if I plug negative 3 in, I'm not going to get an undefined number. So I can plug negative 3 in, plus 3, and I get 0. Okay, so that's going to be the limit here. And if you were to graph this, also in your graphing calculator, you can definitely see that as you approach negative 3, this thing will be heading towards 0. And I encourage you to do that. Okay, let's see, what other one do I want to do? Maybe I'll leave some factoring for you guys to do, maybe for some practicing. Let's do, yeah, so I'll have you guys do 7 and 8. Let's do an infinite one. Okay, so how about number 11 here? So we're going to do, now, you can't plug infinity in. Infinity is not a number, so that's not going to work. So instead what you can do, and here's a little trick, anytime you're dealing with infinite limits, find your highest power of x. In this example, my highest power of x is x squared. And I'm going to go through and I'm going to divide every single thing by x squared, every single term. So I'm going to say that this will be the limit as x goes to negative infinity. And in the numerator, I'll do 2x divided by x squared. And I'll also do x squared divided by x squared plus 5 divided by x squared. So maybe write yourself a note, okay, a little star here. Okay, anytime you're dealing with infinite limits, you can divide out the largest power of x. You got to do it to numerator and denominator, okay? But once you do that, then look what happens. So this reduces, so now I've really got 2 over x, okay? This reduces and just becomes 1, and then I've got 5 over x squared. Well, this takes us back to what happens when you have a constant divided by, x, for example, a variable. As you're saying, x is going to some really, really large number or really, really small number. Well, as that's happening, this whole thing here ends up going to 0. So by definition, it's really important that you understand that the limit as x goes to infinity or negative infinity of, like, for example, 1 over x, that's equal to 0. Just like I showed you. Where did I show it to you? In this example, right? We were using x minus 3. Okay, same thing. So, this limit then, well, 2 divided by x, as x is going to negative infinity, this whole thing is going to 0. This is going to 1, that's great. This whole thing, 5 over x squared, again, as I square infinity, it's just getting larger and larger and larger. So this thing's also going to 0. Okay, so I'm going to really end up with 0 over 1 plus 0, which is 0. Okay, let's do one more. So let's do 13. So I'll have you guys, there's really no good, oh, let's do 2 more. All right, so we're going to do 13. 12 would be a calculator one for sure. And that's what I would probably have you guys use as a calculator. That would be a good one for you to try. All right, so the number 13, the limit as x approaches -5 from the right of 10 over x plus 5. Okay, so there's really no way, if I put a -5 here, I'm going to end up undefined. So really the only thing that I can do is use my graphing calculator. Or have a really good idea of what this graph is. Maybe that's where I should start. So we know that I'm going to have a vertical asymptote at -5. And a horizontal asymptote right about here. Okay, so that's on the actual x-axis because there was no plus k here, so it didn't shift it up at all. Okay, so at -5 I have a vertical asymptote, and then I've got a horizontal asymptote. Okay, and then I believe, if I'm correct on this, if I plugged in, for example, 0, I would get 2. So I think our graph is going to look something like this, and something like this. So that's my guess. So as I approach -5 from the right, this thing appears to be going to positive infinity. Okay, so this is going to have, it's going to head to infinity. So let me just double check that by plugging this into my calculator and making sure that we agree. Setting my table for -5, and I'll change by 0.1. Let's just see what that does for us. So I can see that as I approach from the right, see how originally at like -4 I was at 10, getting to -4.9, it's 100. It's just going to keep getting larger and larger and larger. Okay, so once again, looking at this and saying to myself, I have a vertical asymptote at x equals -5. This thing is approaching infinity. So another one might be you're given a piecewise function. This will be the last one that we do. So given a piecewise function, and I care about looking from the left. Okay, so I really care about this piece right here, right? Because this is where x is less than 1. But I think it's a good idea to either graph it on your graphing calculator. These are ones that we could definitely do. They're just piecewise functions. You're very experienced with that. So at 1, let's see, so unfortunately I have to think about what this parabola looks like. So at 1 it's going to be 2, but that's undefined, or that's not, there's a hole there. Okay, at 0, we're going to be at -1. Okay, that's really all I care about. It's some parabola. Let's see. Where's my vertex? Oh, I guess that is my vertex. Okay, so it's going to, who knows? It's going to look something like this. Just to make sure, -1, 3, 2, yeah. So something like this. And then at 1, it's actually going to be 8. So then just pretend like this is 8. It's just going to take off. It's got a slope of 5. So something like that. We don't really care about that. We just care about approaching 1 from the left. As I approach 1 from the left, it looks like my limit is 2. Right? I don't actually go to 2. It's not actually where it equals 1. Okay? But it's actually it's approaching. So that's doing it graphically. The other way is you can say to yourself, well, this won't be undefined, so I could just plug 1 in. Okay, and you'll still get 2. Just knowing that this thing is not actually at 1, it's actually a value of 8. Okay, so this limit here is going to be 2.